These are examples of fractals in nature. So these are tessellations or fractals in nature. Fractals is the actual repeated geometric shape. And you can see how even in the Nautilus shell, which is this first one over to the top left, that it is a repeated pattern, even though it's not necessarily a geometric shape like a rectangle or triangle. You can see that it's the same pattern, just repeated and repeated. And we get into some number patterns in geometry and algebra too, and there are actually specific number counts that happen over and over and over in creation. You see it not only in animals and plants, you actually see it in the human body, you see it in the galaxy, you see it in a wave of the ocean. The chapter actually deals with sets. In this case, we're going to deal with number sets. This is an example of sets. These are sets of shapes that we have. And so if you look, if you flip over to page 2, we start talking about sets of numbers. All right, so they give you some definitions. All of your definitions in your book will actually have the word definition. I'm not going to give you like, what is a set? And you have to tell me the definition. But what I will say is name the set of numbers. And so I expect you to know what that means. A set is just a collection of objects. In this case, we're going to talk about numbers, but it can be, if I had the set of students in my Algebra 1 class, your names would be listed as that set, right? A set is just a collection of objects. The element of the set is one of the objects in the set. So if I say the element, I'm talking about one object within the set. An empty or a null set, that is a set that doesn't have anything in it. And so you'll notice in your book, these 3 definitions are right at the very top. There is some notation here that they talk about with a null set. All right, so when you see the word null, it means empty. It can be defined with these brackets here, just like that don't show anything in it. That's actually set notation. So when you create a set, you would use those brackets and you would put things in it. If it is an empty set, you just put an empty set of brackets. Other way to define an empty set is a 0 with a line through it, all right? That is the actually notation for empty set or null sets, all right? So they give you the symbol here, empty set. That's the first symbol. The next symbol that we're going to look at is element. This is actually easy to remember because what does that symbol look like? If I were to ask what maybe letter it looks like? E. So element of looks like an elongated E, okay? Then on the other hand, not an element of is just that symbol with a line through it. So element of looks like an E. Not an element is just that elongated E with a line through it. And then of course we've already talked about empty set or null set. So you do want to know these terms because if I were to just say, is A an element of this set, I would actually use that notation. I wouldn't write the words out, an element of. So that would be representative of what that means. The next thing we are going to talk about is comparing 2 sets, all right? Comparing 2 sets. So not only can you compare an element to the set, is it an element of, you can compare 2 different sets, all right? So the first thing you need to know about sets is that they are always notated with a capital letter, all right? So if you look below it, we're going to see definitions of union and intersection. So union of set, if I take the union of 2 sets, I'm going to put both of those sets together, all right? So if I were to create 2 sets here, I would say maybe set A would be 1, 2, 4, and 7. And let's say set B is 1, 3, 7, and 8, all right? So I've been given these 2 sets here, and I want to see what the union is. What is the union here? And so in order to find the union, the first notation would look like this, A, and they would have that elongated looking U almost, B, and that's all it would say. So if I gave you a question, I would just say find this, and what I mean is find A union B. And what I want you to do is I want you to give me everything in both sets. However, you do not write the elements twice. So there are some numbers that appear in both sets. 1 appears in both sets, 7 appears in both sets, right? When I write the union, I'm going to write it in chronological order. By that I mean least to greatest. And I am not going to repeat the numbers if they are in both sets. So if I were to write this answer here, I would say, well, it includes 1 because that's in both of them. It includes 2 because that is in A. It includes 3, that's in B. 4, that's in A. 7 is in both of those, and 8 is in B. And that would be the union of the two sets, where those two come together, and it includes all of them in both of the sets. That is what union means. When you have a union of two sets, you take all the elements that are in all the sets that you are taking the union of. All right? This particular one, and we're still at the bottom of page 2 here, the intersection of sets is what they have in common. It's where they intersect. Like, it literally means where they intersect. So if I were to say, where's the intersection of Ashley Phosphate and Dorchester Road? That's not all of Ashley Phosphate and all of Dorchester Road. It is literally just where the two roads cross over each other, right? Where they have road in common, all right? And so the symbol for this is just like the union symbol, but it's upside down, all right? So when you see this symbol, then that symbol means intersection. So once again, if I were to say A intersect B, and I were to take those same two sets that I just had prior to this, and I said, well, A, that set was 1, 2, 4, and 7. And then if I were to take B, which is 1, 3, 7, and 8. Now I am looking for where they cross over. So I only want the elements that are in common to both, all right? I'm not going to list any other element except where they have in common. So the intersection here would only be what numbers?
1 and 7.
1 and 7. And that is intersection. That's the definition of Venn diagram. Often you'll see this used in literature. So like you'll see elements of a story, other elements of a story. You'll see where those elements cross over each other, right? Or you'll see theme from, like if you're studying Shakespeare, you could maybe study themes from Hamlet, themes from Romeo and Juliet, and there may be some themes that cross over. And so inside the intersection, you'll see that. And you actually literally draw circles that intersect, okay? So if I were to draw a Venn diagram here, then I would draw one circle that would represent my A set, just like I had from the previous page. And then I would draw one circle that would represent maybe my B set. All right, and that would be here. So when you have a Venn diagram, you want to label it. And then for Venn diagrams, you also have what's called a universal piece of it. All right, you have a universal set for Venn diagrams. Now, when you do a universal set, that is what encompasses everything. So the universal set is like your whole entire set of numbers, right? And that's a rectangle that goes on the outside of all your circles, and that's represented by U. And so universal means all the numbers in all my sets, and typically they'll define the universal set. So like for this one, we'll say that the universal set then is going to be 1, 2, 3, 4, 5, 6, 7, 8. All right. So we have those. And then when we did this before, we said that A was 1, 2, 4, and 7. So we have A, and we're going to say that's the same set we just had on all these other examples. All right. And then our B set again is going to be 1, 3, 7, and 8. So we're going to make our B set 1, 3, 7, and 8. So when you do a Venn diagram, you literally just plug your elements into the appropriate circle. Now, if the element falls into more than one of your circles, then you are going to put that element where those circles cross over each other. Okay, so in this case, my A set is 1, 2, 4, and 7. But for 1 and 7, I'm going to draw those in the middle, all right? So I'm going to say, well, 1 is here. We have 2 and 4, and we have 7. That's my A set, right? Because those are all the numbers in my red circle, my A circle, all right? Now for B, 1 I have already written down. I don't write it again. Just like when you write your union, you don't write it again because it's not actually representative of what's going on. We already have 1. We do need to write 3. We do not need to write 7. We do need to write 8, okay? So those are my two sets. Now, here's the deal. I have some numbers in my universal set that are not in any of my two sets listed, okay? So those are actually going to go in the rectangle outside of my two sets that I just listed. So I have 1, I have 2, I have 3, I have 4. 5 has not been accounted for. 6 has not been accounted for. 7 and 8 are already in a set. So this is a Venn diagram. This is a Venn diagram representing my universal set and my two subsets that are inside of it. At the top of page 3. It says, using the following sets, complete each set operation and then illustrate the operation using a Venn diagram. So what we're actually going to do is we're going to draw the Venn diagram first, okay? They did not give us a universal set, so we are just going to draw the two circles, all right? All right, so we have two sets. We have set C, which is, it's going to give me a rectangle. We have set C, which is 1, 2, 3, 4, 5, and 6. And we have set D, which is 2, 4, 6, 8, 10. All right, so we have 2, 4, 6, 8, 10. So I find it easier to draw the Venn diagram first, because if your instructions tell you to draw a Venn diagram, draw it first, and then it's easier to visualize where the intersection is and where the union is. Because very often when you're just comparing numbers back and forth for a list, you miss one. But if you draw the Venn diagram and you've accounted for all of them, then you may actually be able to see what it is. So I am going to look at my sets C and D. 1 is only in set C. Does everybody see that? So if that's only in set C, I'm going to write it here. 2 is in both. So I have 1, 2 is going to go where? In the middle or in the left? No. Yeah, in the middle. What about 3? Left. It's just going to go in C. What about 4? Middle. Yeah, it's going to go in both. What about 5? C, D, or both? C. What about 6? All right. What about 8? D. And what about 10? D. Right? You don't repeat it. You just fill it out where it is. If it's already been accounted for, you don't write it again. So then we can say, what is the union? What is the intersection? So if we look at A here, they want the union. Well, the union is going to be all of them, all right? And so for my union, I am going to say, well, that one is going to be 1, 2, 3, 4, 5, 6, 8, 10. That's union. That's all the numbers listed in those two. So I'm going to say 1, 2, 3, 4, 5, 6, 8, and 10, right? Intersection is only going to be where that term is, where they intersect. So that's even simpler to see once I have drawn my Venn diagram. That is just going to be my 2, 4, and 6. And so I've answered the question. I drew a Venn diagram. I answered my union and my intersection. Subset. One set is a subset of another set if every element of the first is contained in the second. All right? So a subset has to be completely inside the other set. You'll notice what the Venn diagram looks like. All right? The Venn diagram looks like one circle is completely inside another circle. All right? An example of this, if I said A was K4 students at Cathedral, and B was all students at Cathedral, all right? So my K4 students would be a subset of my Cathedral students because all of the K4 students in here, let's say my Busy Bees, for those of you that were Busy Bee, right? Busy Bees completely is inside Cathedral Academy, all right? Now what would be an example that it's not? So what if I said 8th grade is a subset of Algebra 1? That's not true. Why? All of the 8th grade is not in here, right? So that's not true. But if I said 8th grade and Cathedral Academy, that would be a true subset. Every single number within your subset must be in the set you're comparing it to for it to be considered a subset, okay? And you can have equal sets. You can have the same exact elements and the same exact elements, right? So, for example, if I said 8th grade ELA and 8th grade homeroom, those are equal sets. Those are the same exact sets, right? And so you can have a subset, which is all the elements inside another one, and you can have equal sets as well. Subset is actually a symbol that looks like your union turned sideways, right? All right, so they're all kind of this elongated shape. It also has a line underneath it. All right, so when you see one set is a subset of another, then you have this A, and this is the symbol for it right here. This means A is a subset of B. A is a subset of B, all right? And your Venn diagram looks like this. One circle completely inside of another. Now, keep in mind, in this particular circle, you could have elements that are in B, but are not in A. So if I have the busy bees here, and this guy is maybe all of lower school, there's going to be a whole bunch of names in B that are not in A, right? But all of A is included in lower school, okay? All right, so for this set, we have C, which was 1, 2, 3, 4, 5, 6, and D, which was 2, 4, 6, 8, 10. All right? They want to know if 5, 6 is a subset of C. So if I were to look at just the set 5, 6, they want to know, is this a subset of C? Well, let's look at C. Does C include that entire set of numbers, 5, 6? Yes, the set C includes 5, 6. So we're going to say, yeah, this is absolutely true. This is a true statement here. That's true. All right, everybody see what we're doing? All right, so C union D, first of all, C union D, is that a subset of C? What is C union D? Well, that's going to be 1, 2, 3, 4, 5, 6, 8, 10, right? So first we had to figure out what the union is. C union D is 1, 2, 3, 4, 5, 6, 8, 10. That is the union. Is that a subset of C? 1, 2, 3, 4, 5, 6. I have a problem. What's my problem?
You don't have all the numbers.
Right, 8 and 10 are not in C. So this one's going to be false. That one's going to be false. Let's look at C. What is C asking me? What's the question there?
A null set is a set of C.
Yeah, so is the null set a subset of C? What's the null set?
No elements.
The empty set. There's no elements in it.
So would that be true?
Yes. The null set's going to be a subset of absolutely every single set, right? It's going to be a subset of a null set because it's all inclusive. And it's going to be a subset of anything else because all the elements in your null set are in there because there are no elements to compare. So that one's true. What about D? Does D even make sense? No, of course the set has to be a subset of itself because all the elements in the set will be elements in the set. That's just a weird question, right?
So if it has a...
This one's going to be false.
But if it was a subset?
All right, what about E?
True.
That's true.
Yeah.
6 is a subset of D. Now, I will say they have faults, and the reason they're kind of tricking you here, what did they not put there?
They didn't put the element.
Right. So they didn't put your set notation. So if you were to have this on an like standardized test, that's technically a false statement. All right. 6 is an element of, but it's actually asking for subset. So this would be a true statement.
Oh, that's a trick question.
Right. But in order for it to be a subset, it has to be a set. In order for it to be a set, it has to have set notation.
So wait,
So-
it has to be in the middle of like the elongated thing.
This means element of.
Mm-hmm.
So yeah, 6, just an element listed is an element of, right? But in order for it to be asking about subsets, it would have to be a set to begin with. It is not a set, all right? So this one's technically false. If it said element, yes, but it doesn't say element. It says subset question.
So
This is actually true, right? 6 is, that set 6 is a subset of D because by definition it is a set. This is also true. 6 is an element of D. 6 not in notation means I'm talking about an element, so I need to use my element notation.
what if you did the top one with subset of D? Would that still be true?
This one right here? No. So the one that they actually gave you? No. Because this represents an element. So this is an element. This is a set. In order for it to be a subset, it has to be a set to begin with.
So if you wrote it as 6
In the brackets?
and then D,
It is
and
true.
then you put a subset.
Right,
D,
right.
so
Mhm.
true.
It would be true. Correct. So the notation is pretty important here because by definition, subset means you are comparing a set. By notation, 6 is not a set. 6 with brackets around it is a set. While it's a one element set, it is a set. But when you don't list it when you list it this way right here, you're actually talking about an element. And so the importance comes in because when you start talking about set notation, and we're going to use this actually going forward when you get into Algebra 2 and et cetera, if they're asking you for a set of numbers, you have to actually tell them it's a set of numbers. Whereas I could give you an answer and it actually be a list of numbers, and it's not the same thing as defining it as a set. All right, so try some. They're asking you questions here. Page 5, numbers 20, 22, and 24. All right, so the first one, good question, and we're about to actually talk about finite and infinite sets. 1, 3, 5, and you see the ellipsis there, which indicates it keeps going in that pattern. So if you recognize the pattern, those look like those are going to be odd numbers, right? B is going to be -2, -1, 1, and 3. C is -1, 2, 5, and 6. And we're going to talk about odd and even. All right. I really only chose ones from A, B, and C because we're about to talk about number sets with integers and all. So it says 3 is an element of B. Is that true or false?
True.
Right. So the symbol there with a little E looking thing, the elongated E is element. All right. That is true. 3 is an element of B. 3, 5, 7 is an element of A. And because that continues, you may not see 7 there, but what should be the next number if you kept going?
7.
It would be 7. So this one is actually what?
True.
True. All right. 5 is not an element of C. True or false? False. I mean, obviously 5 is right there, so this one is false. All right, so the key to this is these aren't hard, right? It's not hard to look at something and say yes or no. The key is knowing your notation, right? Know your notation. And so the notation that you really want to know here is you want to know element of, not an element of, right? Subset of, not a subset of. And then you want to know your union and your intersection, all right? Union and intersection. Because your questions are going to be that way and you need to know what it's asking you, all right? So we're actually going to turn back to number sets, all right? If we go to... Let's look at the definition. Finite and infinite. So finite means it has an ending, all right? When we think infinite, that's actually a word that we use a lot with the Bible, right? God is infinite. He has no beginning, no end, right? We are infinite in one direction, right? Our souls are infinite, but they were created. So we have a starting point, but our souls are infinite on the other end of it. They keep going forever, even after our bodies are not here anymore. A finite set is a number of elements that is a whole number. So we're about to talk about whole numbers, meaning you can count them. If it is a finite set, you should be able to count them and stop, all right? An infinite set will keep going. In the example they just gave us, they were talking about an infinite set of numbers. They said that A was 1, 3, 5. If they stopped there, that would be a finite set. But they didn't. They added this little guy right here, ellipsis, which means and so on, okay? You'll see this in writing as well. Like, just figure out the rest of it is kind of what they're telling you. There's a pattern here. It keeps going, all right? And so when you see that, that is indicative of an infinite set. It is indicating that you have a set that keeps going. Obviously, I cannot write all the numbers because they keep going, right? So finite versus infinite set. And when you study math, you actually get into number sets that are infinite because that's how number sets work, all right? So number sets, all right? These are number sets that you're going to need to know. Natural numbers. All right, number sets. Natural numbers is what you learned when you were like 2 and you learned to count, right? 1, 2, 3, 4, 5. Those are natural numbers. They start at 1. They are an infinite set because you could keep counting as long as you wanted to, and you would not run out of numbers. You may forget how to say the numbers when you get to a certain point, but you won't run out of them, right? So you see that it says 1, 2, 3 with an ellipsis at the end. It means keep going. It starts at 1, it's your counting numbers, and it keeps going. Whole numbers. The only difference between whole and natural is it starts with 0. All right? While you can't actually count 0 because there's nothing there to count, whole numbers include it. All right? So natural numbers, 1, 2, 3. Whole numbers are 0, 1, 2, 3. And then you have what's called integers. The difference between whole numbers and integers is that integers include negative numbers. Now, something else I want to point out is how the number sets are labeled. This is universal. These are not random letters that they chose, okay? N will always mean natural numbers if you are talking about number sets. Now, does that mean that if you had, number of students in, geometry, that you couldn't use N for it? No. But if you're talking about number sets, N will always mean natural numbers, all right? Whole, that will always be represented by a W, okay? By a W. And then integers, seemingly random, is Z. Integers will always be represented by Z. Very often, if you look in your book on page 3, at the bottom of page 3, you'll notice that it actually has a double line in this notation. So if I were to draw this natural number and I were to actually do this piece right here, that tells the whole world I'm talking about. It has a double line, and that's just what they do. They do the same thing with W's, right? So they'll often just double line one of them, right? Which is really easy to draw, as you can see. And then the Z, they will double line just this piece of it. Okay, so in your book, it actually is drawn that way. I don't expect you to draw it that way. You can just draw the capital number. Natural N, whole is W, Z is always integer. The reason they did Z instead of I is because we're going to use irrational, and irrational is the one that they used an I for. So since you have two that start with I, they chose a different letter for this particular one. So N is natural, W is whole, Z is integer. And there are different things that you would use for these numbers, right? If I was counting people, I would never use integers for that because I don't have negative people, right? And so there are sometimes when these sets make sense and sometimes when they don't, all right? And so when you start doing problem solving, you need to keep that in the back of your mind. If I ask how many people are on a bus and you tell me a negative number, you probably did something wrong in your calculation, right? Does that make sense? And so these kind of help you get in your mind, what am I talking about? Am I looking for an integer? Am I looking for a whole number? All right? If you look at the next page, you have two more sets of numbers. Rational numbers are numbers that can be written as a ratio or as a fraction, as long as the denominator is not equal to 0. All right, so we all know you can't have a 0 in the denominator because you cannot divide by 0, right? If I have 20 people in a class, I can divide it by 5, right? I would have 5 groups of 4. That's easy. But if I have 20 people in a class, I can't divide it into 0 groups because that doesn't make sense, right? You can't divide by 0. So as long as the denominator is not equal to 0, it's any number that can be written as a fraction. Now what this does is this includes every number we just talked about, right? If I have the number 3, I can write it as a fraction. How can I write 3 as a fraction?
You do 3 over 1.
Yeah, 3 over 1. So if I have a whole number, it still falls into this definition because I can put the whole number over 1, no problem. If I have a negative 3, I can do the same thing, negative 3 over 1, still a fraction, okay? These are also, if you have in decimal form, these are either terminating decimals, let's say 1/4. 1/4 as a decimal is 0.25, right? So then 0.25 would be a rational number because I can write 0.25 as 1/4, okay? Repeating decimals, 0.3 repeating. So 0.25 falls into this because I can write that as a fraction. 0.3 repeating also falls into this because I can write that as a fraction as well, okay? So if I can write the number as a fraction, it is a rational number. All right? Now, the notation for rational number is Q, not R, because we're going to deal with real numbers, and that one is R. Okay? So the notation for this, you need to pay attention to notation here, is Q. So we have N for natural, W for whole, Z for integer, Q for rational. All right? Q for rational. Any number that can be written as a fraction. The definition they have down here is all notation definition. So there's actually a way to read this. Q equals A over B. This little line right here would go into words with the words such that. So A over B such that A is an element of an integer, so whole numbers and their opposites. B is also an integer, and B cannot equal 0. So they have just given you the definition in shorthand pretty much right here. All of this is exactly what this is saying right here. Okay, it's just written in all math notation. The opposite of rational is going to be irrational. They list it as Q prime, all right? So they haven't introduced this little prime thing to you. Prime means the opposite of your set, right? So if I was talking about a set and I have that little dash above it, then I mean everything not in that set, all right? I will say that irrational in the math world is most often done with an I, okay? So instead of using Q prime, we're going to use I, all right? That is irrational. Z is integer, I is irrational, irrational. And in the book, it seems like they use Q prime all the time. So you need to know what it means. So if Q is rational, then that little prime above it, which is the little dash above it, means irrational. So if you get something from the book, they're going to use Q prime. If you get something from me, it'll probably have I, because my programming all does I with it. But they both mean irrational. Q prime and I both mean irrational here. So if rational is it can be written as a fraction, then irrational means it cannot. All right? Non-repeating, non-terminating decimals. The most famous example of this is this little guy right here. Okay? Pi, which you'll deal with mostly in geometry. But another example is something like this. He does not have a perfect root. Anything that doesn't have a perfect root is an irrational number. So that means this is going to be rational. This is going to be irrational. Okay? Irrational. And the last thing I want to show you is the Venn diagram of your number sets. It is on page 4. You'll notice that this looks like subsets, right? Looks just like our subset notation. Natural. All of your natural numbers are in your whole numbers. All of your whole numbers are in your integers. All of your integers are in your rational. Irrational is its own little set. Real numbers is all of it. Real numbers is all of it. And by the way, this one is your R. That's why rational is Q. Right, you don't have any homework other than I am going to be emailing home your parents how to access your ebook. All right? If your email is in RenWeb, you will also get that email. If it is not, you may want to talk to your parents about putting your student email in there, or Miss Amy can do it for you. All right? So